So welcome to Lecture 2 in the series Relativity, Electrodynamics, and General Relativity. We studied Newton's world last time and looked at kinematics and a little bit of dynamics as well, and reminded ourselves of Galilean transformations, the transformations between inertial frames, which is a symmetry of that theory. And now we want to work toward analogous results in Einstein's world. Remember the two postulates of Einstein's world, that number one, the laws of physics are the same in all inertial frames. Einstein and Newton agree on that one. But the difference occurs in number two. In Einstein's world, there's a universal speed limit called c, happens to be the speed of light, as we'll derive later in the course, but we'll just be assuming that for the time being for the sake of illustrations. Okay, since there's a speed limit, we know that the additional velocity formula of Galileo, that's so familiar to us, is not true. And if a particular speed is going to be a universal constant, irrespective of the transformations between inertial frames, then space and time measurements are going to have to be distinctly different in Einstein's world from Newton's world. Remember, in Newton's world, distance measurements and time measurements were universal. Okay, so let's just take a look at this speed limit for a minute, just to center ourselves. The existence of a speed limit taxes our imagination. Okay. That certainly is true, because let's consider a flashlight at rest in a frame S prime, which is moving past us at a velocity v. By us, I mean an experimenter in the lab, just standing right here, and S prime being perhaps a rocket ship moving by at a velocity v. The commander of the rocket ship points the flashlight in the direction of the velocity. Okay, and then we sit down in the rest frame and we measure the velocity in our frame. Well, if the rules are those of Einstein, then we know that we'll measure the velocity to be the speed limit. Light moves at the speed limit, it's universal in every frame. In Newton's world, of course, we have addition of velocities. So in that world, the observer would measure a velocity of c, the velocity of light relative to the rocket ship, okay, plus, okay, the velocity of the rocket ship relative to us. Okay, those two velocities will add, and Newton will just get a different expectation than Einstein's prediction. Okay. Now you can make that even more dramatic, the difference between the two, by imagining turning the flashlight around. Okay, so now in S prime, the velocity of the light coming from the flashlight is minus c, just meaning that it's moving in the minus x direction at a speed of c. Now Newton, then, in Newton's world, you'll observe that in the lab frame, and you'll just use addition of velocities. So Newton would predict that the velocity that an experimenter at rest in the lab frame would see would be minus c plus v. Okay, the plus v coming from the relative speed of the two frames. Okay, now in Newton's world, c is nothing special. There's no speed limit in his frame, so he might take v to be 9/10 of the velocity of light, say. Okay, Einstein would say you're going to get the velocity of light minus c in s, no matter what v is. And Newton says, no, I can vary it. In fact, I could even turn it around by choosing v appropriately. Okay, so dramatic difference, and somehow, you know, in our day-to-day existence, we're very familiar with Newtonian and Galilean approximations to space-time, and so we would feel comfortable with this and with this, and not so much with the Einstein result. So we've got to come to grips with how space and time measurements must be different in order to accommodate the universality of the speed of light. Okay, so our first go round on that today will be to look at to make a clock, okay, a physical clock, and just see how it works in its rest frame, and then from the perspective of a moving frame. Okay, so I'll imagine in some cases that my clock is at rest in the frame S. In other cases, let the clock be at rest in the frame S prime, which is moving with respect to me at a velocity v. So here's a clock. It consists of a couple of mirrors, one called A, one called B. In their rest frame, the distance between the mirrors is called L0. Okay, I'll call that the proper distance between the two mirrors because those mirrors are at rest with respect to me. I have to be very careful about these concepts in Einstein's world because times and distances are not going to be universal, so I got to tell you exactly how I make that measurement. That's critical. Okay, and so I'll have a distance L0 between them, and then I'll make a clock by bouncing light from one mirror to the other, and I'll have a single cycle of that clock in the time it takes light to go from mirror A to mirror B and then back to mirror A. So it closes the cycle. Okay, and that's my little Gedanken experiment, my little apparatus. And you see, I make that apparatus in such a way that I can apply postulates 1 and 2 and proceed. I don't know much about dynamics. I don't know much about kinematics yet, so I have to start from the beginning, and I can do that if I use a light ray which travels at the universal speed of light c and see what the implications are. Now later in the course we could construct clocks by relativistic dynamics and find the same result by other more sophisticated methods that rely on the existence of a dynamics which is consistent with the hypotheses 1 and 2. Okay. But we can jump to the answer here just by making this particular clock and have a very elementary discussion where we can emphasize the properties of space and time and not get too many things on our plate at once. Okay. We'll find how time transforms from one frame to the other in this particular case, but time is time. It'll also have to transform in that way for clocks which are made out of more conventional material. And that sort of thing is discussed more thoroughly in the textbook. Okay, so check in the textbook there for more along these lines, and have a discussion. And also in the recitation sessions we'll be discussing things in a more thorough way. Here we're going to get these results for the first time around and proceed. And we don't have a heck of a lot of time to kick the tires. So in the rest frame, okay, the light travels from A to B and back, and so the time for that is just distance divided by speed twice L0 over c, and I call that time interval delta tau. I'll be using tau for proper time. That is the time that an observer measures in the frame in which the clock is at rest. Okay. What I want to do now is to measure the time that passes between these events in the lab frame in which this clock is moving now with velocity v. So over here I show these events drawn apart from the perspective of the lab frame. I have the mirror A. It releases a light pulse that goes to B, bounces off B, and then bounces back to A. And so let's calculate now the time that the experimenter at rest in the lab frame says passes for this pulse to make a round trip. Okay, well the first thing he observes that in his frame the pulse travels at the velocity c, the universal speed limit. Okay. Now we'll redo the calculation from Newton's perspective on the next sheet. Of course, Newton would not write c here. Newton will have to add the velocity of the frame to the velocity of light in the frame S prime and get a different answer. Okay, but we'll find special effects here, special relativity effects, because the speed of light is universal. So my experimenter observes light traveling with the universal speed c from A to B, and it travels in this way from his perspective as this clock moves by at the velocity v. Okay, so it moves from A to B and then B back to A, and in that time interval, the clock has moved a distance, which is just the velocity of the clock relative to the lab frame times delta t, and that defines delta t. Now I can calculate the distance that the light traveled in two different ways. First, it's light. It's traveling at the speed of light, and so this distance A to B, B back to A is just c times delta t. The total time times the velocity of light gives me the distance that the light traveled in the lab frame. Well, alternatively, I can calculate that distance just looking at the picture and doing Pythagorean theorem. I see two right triangles here, okay, where the light ray is the hypotenuse of the triangle number 1 and the hypotenuse of the triangle number 2, and the legs of the triangle are L naught vertical and 1/2 v delta t horizontal. So this distance plus this distance is twice. I have two hypotenuse here, 2 square root of L naught squared plus v delta t over 2 quantity squared, right? That's this distance, and I just do Pythagorean theorem for it. But now I have two ways of calculating the same thing, and so I can use those two ways to calculate what delta t is. Just equate c delta t to the twice the square root and do a little bit of arithmetic. So I'm asking you to provide that arithmetic, okay, and you'll find that delta t is not equal to delta tau being twice L naught over c, but is in fact related to delta tau by a scaling factor that simply depends upon the velocity between the two frames and the speed of light. It's gamma is the scaling factor. It's 1 over the square root of 1 minus v squared over c squared. Now relativity is full of gamma factors, so commit this one to memory, and we'll see it again and again and again. And this result down here is called time dilation. So according to the observer at rest in the lab frame, the moving clock runs slow. How much slow? Well, time is dilated by a factor of gamma. Gamma, you see, is a factor which is always greater than 1. Okay, because it's 1 over the square root of 1 minus v squared over c squared. Gamma is greater than 1, okay, and so the proper time, delta tau, when observed in the lab frame in which the clock is moving by, is dilated by a factor of gamma. Okay. So that's our first look at time dilation. We'll find it again and again. We'll want to understand it better from several different perspectives. We'll look at it visually in Minkowski diagrams. And then when we finally come to the equivalent of Galilean's rules to get from one frame to another, but generalize them to relativity, we'll derive Lorentz transformations, and then we'll derive it again. We'll see time dilation again there. And so after 3 shots at the phenomenon, we'll feel more comfortable with it, and we'll understand it in more detail. We'll see what the sensitivities are and how precise you have to be about the various measurements to predict it properly. Okay, but that's our first go at it. It's surprising. It's interesting. Space-time is very different for Einstein than it was for Newton. In fact, let's imagine redoing that calculation in Newton's world. What would it look like? Well, in Newton's world, the crux of the matter differs only in the detail, of course, that light doesn't travel at a universal speed limit. All velocities are possible in Newton's world, and velocities satisfy Galileo's rule of addition of velocity. So in the lab frame, for example, if you have light which is traveling at the speed c in the frame s prime, in the frame in which the clock is at rest, you would have a velocity going straight up between A and B. And then you have to compose that with the velocity of the frames. S prime is moving to the right at velocity v, like this. And so the velocity of light relative to the lab frame is given by Pythagorean theorem, square root of c squared plus v squared. That's the velocity that Newton would predict for light in this little clock made of mirrors and light beams. So then you redo the calculation, stating that this distance from here to here is given on the one hand by the velocity of light in the lab frame times the time interval that passes in the light frame, and you equate that to the distance that the light travels when written in terms of L naught and V delta t. So do that, okay, and solve for delta t, square both sides and isolate delta t, and you'll find that delta t is the same as delta tau. You'll find that delta t is L naught over 2c, which was delta tau. So in other words, the clock, of course, does not slow down. Times are universal in Newton's world, and this particular clock satisfies that criteria. We knew it had to be that way because time is universal, as we discussed in the previous lecture. Okay, and we just verified that if you use Newton's rules for in Galilean transformations, that you'll find that time is universal. Okay, that's the old way, and we see it just clarifies the fact that the crux of the matter. Why is Einstein's prediction so unique? It's because of the universal character of the speed of light. That the speed of light is the same in both frames, and that means that space and time measurements must be different between the two frames. Okay, so let's pass on then to the measurement of distances. Well, I'm going to do this again, just taking advantage of the fact that now I know that time dilates between frames, and I'll just reorient my clock to make it a measurement of space rather than time. So I'm going to take my clock, okay, which had a certain orientation. I'm going to rotate it by 90 degrees. Okay, so now the mirrors A and B are aligned in the direction of the boost V, not perpendicular to it. Okay, now rotating the clock, of course, doesn't change its operations at all. Okay, its period is still delta tau. The measurement of the time that passes as observed by the observer at rest in the lab is still going to satisfy time dilation. Rotation of the clock can't matter, okay, because space is isotropic. Rotations are symmetry of the world, and so I know how my time transforms. We just derived it, and I'm going to use that to see that spatial measurements must transform as well. In particular, I'm going to call the distance from the mirror A to mirror B as measured by the experimenter, okay, and I'll call that L, okay. I'm not going to assume that it's L naught. L naught is the distance between the mirrors in the rest frame of the clock. Now the clock is moving in the lab frame at a velocity v, and I want to know what the experiment at rest in the lab frame would measure for the length of the clock, and I'm going to call that L, okay, and relate that to L naught, the proper length of the clock, and see the relationship between the two. So here it is. Here are the three events that we showed up here. Light getting to B, light reflecting from B back to A, and so I show them here. So after a time delta t1, light moves from mirror A to mirror B. I show that here. Here's the light hitting mirror B and being reflected back. And now I wait another duration in the lab frame, a time delta t2, and light gets back, okay, travels back to the mirror A. Okay, and that's the full cycle of the clock. I know that in the lab frame that takes a time delta t, and that's related to the proper time of the clock by time dilation. So let's take a look at this in detail. Let's calculate delta t1 and delta t2, and their sum is delta t, the time for the cyclic motion of the clock in the lab frame, and so I can calculate it in these terms as well, and use that fact to calculate L in terms of L naught. So let's get the equation for delta t1. Okay. Well, the light moves in the time delta t1, a distance c times delta t1, of course. And here it is from the perspective of the lab frame. It moves a distance L plus v delta t1. Okay, the clock is moving as well, so it has to move the length of the clock plus how far the clock has moved in that distance. So I've written it down here. Light reaches b after that duration. And then similarly, now the light is moving in the opposite direction, and so I can calculate delta t2, the time between these two snapshots, as the distance times delta t2. That's the distance it travels between these two situations. And I see between these two situations, light has moved the length of the clock minus the distance that mirror A has moved toward the light. So it's L minus V delta T2, just looking at the picture. Okay? And so here you see I can solve for delta T1. Just looking at it, I see it's L divided by C minus V. And similarly for delta T2, and I can add them up. Do that arithmetic for me, and you'll see that you'll get gamma squared times 2L over C. Okay. Well, now let's use the fact that I know time dilation. Okay, that the delta t, the period of the clock as measured by the lab frame, is related to the period of the clock in the moving frame, the proper frame, by a factor of gamma. So put that in here. So delta t is this. Put that here. Okay, and then solve for L in terms of L naught. That's what we want. Okay, what's the relationship of the length of the moving clock to the length of the clock at rest? And I see the factors of gamma cancel, and I see that the length of the moving clock is the proper length divided by gamma. Gamma is greater than 1, so this is a contraction factor, and it's called Lorentz contraction. Okay. Okay. So I see, in order that the speed of light be a universal constant, time intervals have to dilate, okay, and spatial intervals have to contract, okay, and that's true for spatial intervals in the direction of the relative motion of the two frames. Spatial measurements transverse to that direction are unchanged by the relative velocity. And look at the textbook for the discussion of that. That's sort of pretty obvious. Right, but check it out there, just to be careful. Okay, just be careful. A lot of surprises here, so we have to have some care. I won't look into the transverse directions here, but you can check in the textbook and in the problem sets that the transverse distances are invariant to the boost or the transformation between the moving frames. So now we have Lorentz contraction. First shot at it. We'll see it again and again and look at it from different perspectives. So the last effect we want to look at now is to ask the question. We went to a lot of trouble to synchronize clocks on a grid work in one particular frame. Okay. In Newton's world, of course, if you synchronize them in one frame, you synchronize them in all frames. But we want to ask if that's true in Einstein's world as well. Well, again, the universality of the speed of light is going to change things, okay, and make the synchronization of clocks, which are separated in the direction of the boost, the velocity v, frame dependent. And that's what we want to show here. This effect goes hand in hand with time dilation and Lorentz contraction. So to have an understanding of those two effects properly, we have to understand relativity of simultaneity as well. Okay, it's critical to do that. So here I imagine a couple of clocks, number 1 and number 2, at rest in my moving frame S prime, and I synchronize them. That means I find the distance halfway between them, and I have a pulse generator that sends light in every direction. Okay, and as soon as the light reaches 2, I give it a time, maybe high noon. And as soon as the light reaches the first one, I give it a time, high noon. The same as 1 and 2. I synchronize 1 and 2, and I do it in this particular way, which is which uses light and distance measurements in a very elementary form. Okay, so light spreads out from 1 to 2 in the frame S prime. It travels at the same speed in this direction as that direction, so it's sensible to synchronize the clocks in that particular way. I can take a snapshot of the face of the clock 2 when light first impinges on it, and call that high noon, share that between frames, and do the same thing at 1, share that information between frames, and everyone agrees that when light hits 2, it's high noon, and when light hits 1, it's high noon. So I've synchronized my clocks in S prime. Okay. There's no time difference between the clocks at high noon. They're synchronized. But now my observer at rest in the lab can question whether they're synchronized in his frame. Well, he just looks at it and says, no way. Okay? Because he sees, from his frame, okay, he sees the light ray moving toward 1 at the speed c, at the universal speed limit, c. He sees c the same way that S prime saw c. So he sees light moving at that same universal speed toward 1, but 1 is moving toward the signal generator. Okay, so he'll find a certain amount of time that passes in his frame for that sequence of events to occur, and then he'll notice that over here that if he wants to calculate the time that passes between the emission of the light here and the capture of the light at 2, that he'll get a larger answer because, well, clock 2 is moving away from the signal generator, and the speed of light is c, the same as the speed of light going in the other direction. So he says that there's a time that passes in his frame between the two events. He concludes that the clocks are not synchronized relative to his clock, and so the synchronization process that worked in S prime will not work in his particular frame, and the simultaneity is relative. It's frame dependent. And now he'll do a calculation to see how much time passes between the capture of light at 1 and the capture of light at 2. Well, that's easy. It's just the calculation we've already done. He wants to calculate the time for the pulse to hit clock 1. So the light travels a distance c times t1. I'm saying that the pulse starts out at the pulse generator at a time 0, say, and then I calculate time from there. Okay, that's a convenient way to do it. So c t1 is then equal to the distance the light traveled. Well, light traveled half this distance. Okay, that's L over 2. He knows about Lorentz contraction, so he knows not to write L naught over 2 because this is a distance as observed in his frame of a moving frame. So he writes L over 2, and then minus V times T1. This clock is moving toward the pulse generator, and so the light travels a shorter distance by the movement of the detector, the clock 1, by VT1. And then he does the same thing for 2, and the only difference is that the minus V becomes a plus V. This clock is racing away from the pulse generator, and he writes down that for T2. Okay, he knows full well that T2 is greater than T1, and he solves this equation for T1, this equation for T2, takes the difference. Again, I'm letting you do the arithmetic, but of course it's the same arithmetic we did in time dilation, so I know it's going to be gamma squared LV over C squared. But do it, just do the arithmetic. Okay, it's just one line. Okay, and so according to his clocks, okay, time has passed between the two events, and so he disagrees with the synchronization process, but he wants to write the time that passes in his frame between the synchronization of 1 and 2 in a more universal fashion. Well, you see, here's L. Okay, that's his measurement of the velocity, of the distance between 1 and 2. And of course, the universal characterization of how far apart they are is their proper distance. If you tell me the proper distance then everyone agrees on that, because everyone understands to measure a proper distance, you go to the rest frame of the two clocks and put down your meter sticks. So there's no V dependence in it. You want to pull that V dependence out and just write it in terms of L naught. Okay, so we do that. So L is related to L naught by Lorentz contraction. So I'll swap L for L naught over gamma. That swallows up one of these gamma factors here, and I'll get delta T is equal to gamma L naught V over C squared. Okay. But now S wants to go a little further and say what's the time difference in the frame S prime that corresponds to a time difference delta V in his frame. Okay. Okay. And so well, he knows time dilation. Okay, so he knows to pass from delta T to delta T prime. Okay, he'll just have a factor of gamma to represent time dilation. Okay, he knows that his delta T that he measures will be related to delta T prime, the time that passes in the rest frame of the apparatus. Delta T will be gamma delta T prime. Okay, how much time does he say passes in the moving frame between events 1 and 2? So you'll see this gamma gets canceled out. Delta T is gamma delta T prime, so delta T prime is just L naught V over C squared. Okay, so that's the amount of time that S says that passes in S prime. Okay, so he disagrees with S prime. He says that according to his clocks, the clocks in S prime are not synchronized, and he'll tell you how much by which they're not synchronized. Okay, from in the formula, delta T prime is equal to the distance between the clocks, the proper distance between the clocks, times V over C squared. S says, okay, since this time is positive, that the leading clock in S prime lags the trailing clock by the amount that he calculates, right? Delta T prime is L naught V over C squared. It's positive, and so the leading clock must lag the trailing clock by this quantity, because I calculated the difference between the time at 2 to the time at 1 as measured in the lab frame. Okay. Okay, so we learn from this that when it is a particular time t in the lab frame, the corresponding time in the moving frame depends upon x prime, right? Because L naught is the distance between the clocks in the frame S prime, and so in general, L naught is a distance in S prime. That I would generally just call that as x prime, and I see that T prime varies as x prime V over C squared, replacing L naught by x prime. Okay. So when I say it's a particular time in the lab frame, that does not pick out a particular time in the moving frame. We say space and time mix. Okay, space and time mix, because the time in the moving frame is now given by T prime, which varies with x prime as x prime V over C squared, a linear effect. Okay, okay, and so now I see that S says that the clocks in S prime are not synchronized according to his time t, and the lack of synchronization is then given by this particular formula. When it's time t in his frame, t prime, the time in the moving frame, is given by formula x prime v over c squared. Okay, and that's the relativity of simultaneity, and we'll come back to it several times. You see, it just follows from the universal character of the speed of light, and so it goes hand in hand with time dilation and Lorentz contraction, and to have a full, consistent understanding of how space-time measurements transform from one frame to another, we need the three different effects, okay, of time dilation, Lorentz contraction, and the relativity of simultaneity. Okay. So in recitation, we'll do some problems on this subject and try to get used to these effects. We'll do it again with a minimum of algebra, so we'll really grease our cerebellums and prepare us for more complex and interesting effects down the line. Now in our next lecture, we'll look at a visualization of these effects, Minkowski diagrams, and so see you then.